n value, n can be 4 or 5 or even can be 2. Okay, but normally people use 4 or 5. And the number of G is number subgroup. Okay, and is okay, this is 4 or 5. You must fix lah. If you use 4, continuously using 4, meaning that every time you take sample, you take 4 or you take 5. G is subgroup number. Okay, subgroup number normally between 20 to 30. Okay, 20 to 30. Why? Because we want to make sure that it can represent distribution. Normally, to have a distribution, you need at least 20 subgroup. Okay, it will be good if you have 30, but sometimes taking sample is expensive. Okay, so if you have subgroup number of 20, you already can have, you can plot it. You can plot it histogram. Okay, to show the pattern lah. Okay. Okay. So another chart, okay, another chart that we have is X bar chart and S chart. X bar chart and S chart. Okay, so I mentioned just now the performance of the control chart. We decide how many samples to take, how many subgroup, and also we also decide the control limits. Okay, how do we decide control limit? Normally, control limit is decided based on plus minus 3 sigma. Okay, when you have a control chart. Okay, this is common for any control chart. You have central line. Okay, you have central line. For X bar chart, it will be X double bar. Okay. For example, you have X double bar. Okay. So on this side, you're going to have X double bar, which is center line. So meaning that X double bar will be plus 3 sigma. Okay. For X double bars, this sigma we're going to be X sigma X bar. Okay. On this side, the bottom part, just double bar minus 3 sigma X bar. So now we want to know how good is this chart. Okay, so we call it performance metrics for the control chart. Okay, of course this one we can simplify like we have discussed earlier, X double bar plus A2 R bar. Okay, so this one will be simplified, X double bar plus A2 R bar. Okay, similarly also at the bottom. Okay, so that is just a review there. Okay, now, okay, as I said that when we design control chart, we want to see how good is the control chart of our what we designed. We decide the control limit, we decide sampling frequency, we decide sample size. So one measure that we use, okay, we call it average run length. Okay, average run length. Okay, this is a measure how good is our control chart. Okay, for short control chart is meaning that the chart that we have seen, for example, X bar chart. X bar chart is short control chart. Okay, so ARL, or what we call average run length, is a measure how good is the control chart. So we have ARL1. Okay, this is normally we call it ARL0. Okay, this is ARL0, and we have ARL1. Okay, what ARL is doing is ARL0 or ARL node here is referring to when a process is stable. When a process is stable, we are expecting there will be no false alarm. No false alarm. Okay, just 1 minute. Somebody coming to deliver something. Okay, sekejap. Okay, sorry. Okay, so I say just now that the performer measure, we have average run length. Okay, average run length. So apa maksud average run length? Okay, if you have control chart, okay, let's say the process is stable. Okay, ARL node is for stable process. Okay, remember that ARL node is for stable process. A measure for stable process, meaning that process has no problem. Okay, but what happened is because of control chart is based on sampling, okay, there will be situation that there will be false alarm. Okay, apa yang berlaku false alarm. Let's say the point is moving up and down. Yeah, I bet this cross line is meaning that the observed data. So there might be the process is stable process. Suddenly there will be 1 point here. Okay, this 1 point actually coming from stable process, but because of sampling, okay, imperfection in sampling, so we have what we call it false alarm. Okay, false alarm. False alarm, this is like when you are having no fire, but suddenly the alarm is ringing. Okay, false alarm. So ARL is a measure how long that the stable process will run until it is the first time that false alarm will trigger. Okay, so if we have this is, for example, this is number 1, this is number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9. Let's say this number 9 is the trigger. But actually ARL for stable process is going to be very long. Okay, so if this is the case, okay, let me make correction here. It will not be here. It's going to be very long. Maybe, okay, maybe on average, it's going to be, let's say, okay, let's say I put it 300. After running 300, average run, after run 300, you may have 1 point. Okay, so maybe you run another process, okay, that might be happening not at 300, it might be happening at 400. Okay, maybe another process happening at 400. Okay, so maybe another process is running at 350 and so on. But on average, ARL is the average run length. Okay, average run length. So if we have enough repetition, okay, we're going to have, okay, 370. This is if you run simulation, also we can get this number. If we run random number simulation, so let's say the first one is 300. Okay, maybe the second one will be 400. Okay, the third one will be 350, meaning that the first time it will be outside control limit. The process is stable, supposed to be every point is inside, but because of sampling, they might be having false alarm. Okay, might be having false alarm. So continue. Okay, maybe another one going to hit at 410, but on average, if we add all these, if we have enough sample, let's say we have run the process 30 times or 40 times, 50 times, the more we have sample is closer to 370. Okay, so finally, on average, ARL for stable process, we call it ARL node, is equal to 370. Okay, how theoretically we can prove this? Okay, theoretically we can prove it. Okay, I go back to our famous normal distribution. Here we have our normal distribution. We have this. Okay, so we say that if we have plus minus 3 sigma, okay, so you have this area outside this. This is considered going to be false alarm outside. The process is stable. So you have 3 sigma here, okay, plus here. You have, okay, we are referring to the center here. So minus 3 sigma. Okay, so the area under the curve, okay, of this normal distribution, this area, okay, this area under this curve will be 99.73. Okay, I think everyone know about it now. Okay, 99.73. So this is meaning that if we have 1 minus 0.9973, okay, this is our alpha actually. This is our alpha. Or in another way, probability. Probability 1 point of plot out of the control. Okay, we want to see what is the probability of having this. Okay, so meaning that 1 minus of the inside is going to be 0.0027. Okay, so ARL node, it will be 1 over P. Okay, 1 over P, this one, 1 over P. P is this value, okay, this value and this value. So P divided by 2 lah, we have two-sided. So 1 over P, meaning the P here is 0.0027. This is for stable process. Okay, what do you get this number? 1 over 0.0027. Okay, can somebody help me? Put in your calculator.
370.
370, okay, 370. So that's why
0.37.
0.37, okay, 0.37. So we can round off this. So we can say 370, okay, 370. Also 370 is false alarm, okay. So on average, if we run a stable process, there will be 1 false alarm every 370. Okay, every false alarm. So process has no problem, but the control chart showing that 1 point outside. Understand ke? Boleh faham ke? The concept of performance measure for control chart based on ARL. Hello, can you respond to the chat box whether you understand or not?
Doktor,
Yes.
yang false alarm tu dia occur setiap 370 ke dalam range 370 yang next tu dia boleh jadi bila-bila masa?
Yes, dia boleh berlaku anywhere, but normally on average, sama tu saya kata tadi, maybe dia berlaku first time 300. Lepas tu you stop the process because you found out that there is nothing wrong with the process because of sampling it create false alarm, and then you move on the process. The next one maybe berlaku pula at 400. It's not going to be exactly 370. 370 is average. On average, maybe the next one you stop the process at 400 and then you investigate the process. Oh, nothing wrong. Actually, it was false alarm. You run the process again. Now it happened at 350 false alarm. And then you check, there is no problem, and then you continue running the process. So maybe the number keep fluctuating. Maybe sometimes you got 410. On average, you take this all average. Okay, you add all the number, add, divide by how many. You get this on average, the run length for the first alarm to happen, first alarm to happen, after you done reset, you stop, you're going to get 370. This is the number. Theoretically, it is explained in terms of what is the area outside the control limit, which is 1 minus 0.9973 is equal to 0.0027. Because of probability of outside is P, 1 over P, finally we also get this number. This one is if you test it in real life, you will get this. But if you run simulation also, we run simulation using random number, also we got this number. Close to this number, okay, 370. If you run long enough sample, okay, you will get these 370 numbers. Okay, so your question is whether it's going to be exactly around this. Yes, it fluctuates between 300, 400, 350, 410, but on average it's 370. Is it clear?
Yes.
Okay. So I don't know, is there any relationship or not with MH370? Maybe consider, what happened to MH370? Is it following this theory? Or somebody hijacked the aircraft? Okay, it could be false alarm, but anyway, it's a big loss. Okay, so maybe the number 370 is explaining the false alarm happening here. All right, so what happened if the process is unstable? Let's say a process having problem. When a process is having problem, we want to quickly detect as quick as possible. Okay, as quick as possible for a process to be detected it is out of control. Okay, so that stable process, we use it ARL 1 minus beta. Okay, this is for unstable process. Okay, unstable process. Stable process sometimes you call it in control. Okay, unstable process we call it out of control process. Okay, for unstable process already have problem. Okay, so a process having a problem, we want to detect as quick as possible that a process is having problem. Okay, so how to measure how quick it is being detected? We use ARL1, 1 minus beta. Okay, over here 1 minus, this is the p value, alpha. Sometimes they call it alpha. Okay, same thing. So in here, what we want is as long as possible. Okay, when the process is stable, it should be as long as possible. But when the process is unstable, we want it as quick as possible. Okay, so studies has been done using simulation. What they do is, like this is the shift, the shift in control chart. In the control chart, you have a shift. Okay, you have control chart, you have a shift. This is 3 sigma shift at this point. This is minus 3 sigma shift. Shift means that, okay, your sample suddenly shift up. Okay, this is shifting. Okay, shifting. So we want to know how quick is the control chart to detect when there is a shift. There might be a shift of 0.5, 0.5, 1, 1.5, 2, 2.5, 3. Shift 3 meaning that immediately is out lah. Okay, so your control chart should be able to detect this. Okay, if there is shift 2, okay, somewhere here, okay, you have this is 2, this is 3, this is 1 shift. If one shift here, okay, meaning that this process shifted to this point. Okay, so what we want to see, how quick is the ARL, okay, to detect the shift. Okay, the faster it can detect, it means a better control chart. So in here, if the shift is 1, let me see. I think this example is showing how quick it is. In terms of K sigma, K is this number. Okay, so K equal to 3, K equal to 0.5, K equal to 2, K equal 1.5, K equal to 1, and so on. Okay, so 3 sigma, 2.5 sigma, 2 sigma, and so on. So average run length. Okay, so so we see that if the shift is, let's say this one, the shift is 3 sigma shift, okay, and depend on n number. This is n equal to 1, n equal to 2, n is sample size, n equal to, and at different n, okay, at different n values, okay, so we see here, okay, how n value influence how quick that we can detect. Okay, let me see, just take for example ARL 10. Okay, let's say after 10, at a point number 10, okay, who will hit faster. Okay, so if you have 2 sigma here, okay, 2 sigma here, this is 2 sigma, and you have 2 sigma here, 2 sigma here. Okay, it shows that a bigger sample size, it is faster to detect. If you have only one, you're going to delay in terms of detect. See here, if you have 2, n equal to 2, you can detect at ARL equal to 3. Okay, if you have n equal to 1, this one, you need 10 points to detect. Okay, it delay. But if your sample size is 16, okay, you're going to detect very fast. Understand or not how the sample size influence the speed of detection of out of control? Hello, are you following me or not? The sample size influence, okay? The sample size influence how quick that you can detect out of control. So if you take more sample, because we know that sample, I say just now, you can have 4 or 5, right? Normally people use 4 or 5. If you take 5 or 4, for example, okay, you are detecting a shift of 1.5, okay? Okay, where is the shift of 1.5? Shift of 1.5 will be in the middle of control chart. The middle half, middle half. Okay, this is the middle, this is 3, this is 3. So now let's say you are running a process, is running, suddenly the shift is happen like this. Okay, so then there will be a point, will be outside, will be outside. So this shift, okay, assuming this shift is, let's say I take this easy number here, 2. Okay, let's say the shift here is happening at 2. Okay, the shift from here to here, okay, let's say this is happening at 2 sigma shift. Okay, so meaning that this line, okay, this line, okay, the shift is 2 sigma. So what I'm comparing is if I use n equal to 2, okay, I will need, okay, more than 2. If I use n equal to 2, okay, the first time I will detect, okay, detect this will be 2.5, a point which is 2.5 here. Okay, there will be something there. Okay, on average, okay, consider it's quite fast, quite fast. But if you use only one n equal to 1, okay, you will detect only after this point. You will detect after 7. Okay, at 7, meaning that 1, 2, 3, 4, 5, 6, 7. Only here you can detect. Okay, it takes longer time to detect. Okay, longer time to detect if you have small n. Okay, n equal to 1. But if I take bigger n, for example, I take n equal to 16. Okay, this is n equals 16 is a lot, you know, every sample you take 16. So normally we take only 4 and 5, but now let's say we take 16. You're going to detect immediately. The first time they're out, okay, we already detect. Okay, so n will influence the detection of ARL 1. Okay, same also actually for ARL 0, there's no issue because the process is stable. Okay, there is no issue. But this is already we say 370. Okay, the process is stable. But when the process is unstable, it depends on instability. How much is unstable? Is it 0.5 sigma? Is it 1.0 sigma, 1.3 sigma, and so on? Right. I hope that you get the idea how we can evaluate performance of control chart. Okay, so it's good to have more sample taken, but actually more sample taken is costly. Okay, because every time we take sample, we do testing on the sample, it is costly. But that's why some people try to use a small sample size. Okay, another measure, we call it average time to signal. Average time. Okay, now we are looking at the time. So ATS equal to ARL multiplied by H. What is H? H is equal space interval of time. Okay, maybe you say I take sample every half an hour. So H will be half an hour. Okay, let's say your ARL is 10. Okay, 10 multiply every half an hour you take sample, 30 minutes. Okay, so it means that average time to signal will be 300 minutes. Every 300 minutes, you can expect that the signal of unstable will be triggered. Okay, so this is when we express in terms of time. Also, we can express in terms of number of individual unit sample, which is I. Okay, I, N is number of individual unit, multiply ARL. So we can express differently. Right, okay, let me move on to another control chart. Okay, any question before I move on to S chart? Okay, we have seen X bar chart, R chart, but now we move to S chart. Okay, S chart is standard deviation chart. Okay, standard deviation. Okay, S, if you take sample, sometime for population, you take it as sigma. Okay, for sigma. Okay, so although X and R are widely used, occasionally it is desirable to use standard deviation. Okay, it's desirable to use standard deviation. Okay, standard deviation chart. Okay, so this is where we use S. Okay, so we couple X bar and standard deviation chart instead of X bar and R. R is range. Okay, range chart. Okay, so why we use S? Okay, this is because okay we want to have a better accuracy because S chart is more accurate. In order to use S chart, N must be moderately large, which is greater than 10. Okay, greater than 10. Meaning the sample size we take should be greater than 10. Okay. So, and the sample size, if the sample size is variables, okay, we can also use S chart. Okay? Sample size is variable, meaning that sometimes we take 10, sometimes we take 8, sometimes we take 15. We can use S chart. Okay, we can use X chart. Okay. Okay, how do we prepare this X bar and S chart? Okay, so we have to understand this theory. Okay, construction of X bar and S chart. Okay, so as usual, what we do is we take 25 sample. Okay, 25 sample, which is this is actually the G lah, the G. Okay, in the book we call it sample. So we have calculated the sample average and sample standard deviation for 25 sample. Okay, so okay, let me show. I think in terms of example, maybe easier for you. Okay, let's say this is example of data taken. Okay, inside diameter measurement of automobile engine piston ring. Okay, piston ring. So we have sub sample number. Okay, sample number 1, or this is basically is a G value. Okay, the G. Okay, G. G equal to, in this case, the G is equal to 25. See, we have 25 here. So 25 subgroup. Okay, 25. 25 subgroup. Okay, we have here one observation. So let's say sample number 1 we take in the morning, 8 a.m. So we are taking N equal to 5. Okay, this one is N equal to 5. Okay, so sometimes people get confused when calculating the average. So the average should be, you take all this number, okay, all this should be plus in order for us to get the average X bar, okay, X bar. So this is what you get, the average of these 5 values, you get 74. See, this is X bar. Okay, when you go for example, 9 a.m., you take another 5. Okay, so this is the average value for X bar. So we have X bar here, we have the S here. Okay, the S. S is standard deviation for sample. We continue doing this, okay, continue doing this for 25, okay, for 25, so until here. You do the same thing, you get it here. Okay, this is the X bar. Because we are now using X bar S, okay, so how to get S? Okay, this is standard deviation, SI, SI meaning that this is S1, this is S2, okay, and so on. So the S is given by this formula. Okay, this is the how to get the S, which is the standard deviation for that 5 sample. Okay, is it enough or not to have, according to guideline, how many sample we should take? What should be the N? The guideline says.
And 10, more than 10.
More than 10. But how come in this example you give only 5? Because just academic example to make it easy. Okay, N should be greater than 10. Okay, don't confuse. In this example they give you only 5 because why? To make it simple. Okay, to make it simple, it should be 10. Okay, not 5. But it shows you 5 by because to make it simple calculation. Okay, but it should be 10. Okay, assume that N is enough. We have to assume that N is sufficient. Okay, sufficient to use S chart. Okay, sufficient to use S chart. So how to get S then? So S is coming from here, which is the observed value for everyone, minus X bar square, summation of those divided by N minus 1. So what you do is, okay, in this case, you already have this number, okay, 74, okay, the S1, okay, I'm referring to the first number, I'm referring to this number, I'm referring to this, okay, S1, okay, the S1 equal to 74, okay, 0.03 minus, okay, minus the average here, 74. Okay, this number, the average here, 74.01. Okay, and then we continue, okay, using this formula, okay, this formula, okay. So we continue summation of that. So don't forget to get it square here. Okay. So the next number is 74. Okay, 0.002. Okay, minus 74.01. Okay, you square that and continue until you get the last value. Okay, the last value is 74.008. Okay, minus 74.01. Okay, square that. Okay, divide by. Okay, divide by. So you have here divide by N minus 1. Okay, in this case is N is 5. Okay, So 5 minus 1. Okay. So now you get this as 1. Okay, as 1. So repeat the same. Of course, manually is going to be tedious lah, but if you put it in Excel, you just copy the formula, you get the answer. Okay, continue this. And then what you need to get is the averages. Okay, the average of S. Okay, S bar. Remember, this is S bar. S bar is the average of S. Okay, average of S. So, okay, so the formula that we use to develop the control chart is this one. Okay, this is S chart. Okay, so this you also can use the standard values. Okay, this is coming from table. This is B6 and B5 is coming from table. That also can simplify our preparation. Okay, so you can have this is for S chart, for S chart. Okay, the center line will be C4 sigma, or sometimes we call this the average of S lah, S bar, the S bar. Okay, so you can have this B6 sigma, and this is B5 sigma. Okay, so this one is C4 sigma. Okay, there are times where we need to use estimated value. For example, when there is no standard is given for this sigma, okay, so we use this, like what we did in this case. In this case, we don't have value, we can estimate this. Okay, we estimate this as S bar there. Okay, so it's estimated. Okay, summation of this divided by how many subgroup we have. In this case, M is the number of subgroup. Sometimes I call it G, it's the same. So where normally we use it from preliminary sample when the process is still unstable. Okay, so when the process is stable, we can use this value. Okay, this value. This is for a stable process, or sometimes we call it for a revise. Okay, this is for a revise. For a revise S chart. Okay, S chart. Same thing that we do for X bar chart, we discard the unstable data and we recalculate again the new, okay, the new limit. So this is, if we plot, it will look like that. This is S bar. This is B4 S bar. Based on estimated data, And this is B3 S bar. Okay, so remember that when we do control chart, first we have the trial. After we remove the assignable cost, we revise. Okay, we have a revised control chart. Okay, the same thing also for S chart. S chart, X chart, R chart. Also going through the two phases. Okay, phase one is trial, second phase is revise. So for the revised one, we can use this one. How to get this? The important part here is how to get S bar. Okay, S bar here. S bar here is this one. Okay, where the summation of S, here we have considered removing the unstable or out of control data. So, okay, okay. So for X bar chart to be used together with S chart, okay, we are using this formula A3 S bar. Okay, remember this is not R bar, S bar. So it's going to be X double bar for upper control limit plus A3 S bar. Previously in X bar chart, okay, X bar and R, what we used was X bar plus A2 R bar. Okay, but this is S chart. This is in the case of X and S. Okay, so the bottom part is minus. Okay, minus lah. The difference only this minus. Okay, this one is positive. Okay, same thing also here, plus minus. So this is A3, this is A2 for the case of X chart. Okay, so for S chart, we already have it here. Okay, this is S chart. B4 S bar, B3 S bar. Okay, let's see this example here. Construct an X bar and S chart using piston ring inside diameter of the table 6.3. Okay, table 6.3 is already given earlier. 6.3, this is 6.3. Yes, this data is given. Okay, after measuring 25. Okay, in your books, this G is they call it M. The M, same thing, subgroup. So this is N equal to 5, and the S X bar already taken here, average here, X double bar, S, okay, individual S, and then finally S bar here. Okay, so based on this data, okay, X double bar, we get this finally, this is the central line. Okay, so meaning that we have center line for this chart X double bar equal to 74.01. Okay, so and S also we have calculated the 0.2351. Okay, 2351. If you look at here, 2351. Okay, this number. Okay, you have 2351. Okay, 2351. Yeah. Okay, so divide by 25, you're going to get 0.0094. So okay, you see here, you get it. So you get now X bar, and you already get X double bar, and also you got S bar. So now we are ready to provide X bar chart. Okay, using this formula. See this formula? Okay, very simple, simple formula. Simplified. Okay, A3 S bar. Okay, A3 from table, you can get this number. Okay, and the difference here is this is positive, this is negative. Okay, so okay, so that is X bar chart with S, but now S chart. Okay, the S chart. So we have B4 S bar. So this is what we get now, this value. B3 S bar, this is the value. Okay, so plot the chart. Okay, now it's given. So it shows that in this chart there is no out of control. So this limit could be adopted for a phase 2 monitoring. Okay, so there is no point outside. Okay, no point outside control limit. Okay, this X bar, this is S chart. Okay, so actually in control chart for R and S, if the point is below, it shows its good performance. Okay, we want it R value and S value, low value. Okay, low value is good. Okay, because it shows that low variability. All right, we can also estimate. Okay, we can estimate the process standard deviation. For example, we want to know what is the process standard deviation. We can use this formula. Okay, I explained this earlier in okay, using process capability. We can estimate that this value of sigma bertopi ni, okay, can be estimated from S bar, we already have the S bar, divided by C4. C4 is from table. So now we can estimate the process standard deviation. Okay, the sigma mean process, coming from the estimate the population. Okay. Okay, so in this case, is given as 0.001. Okay, if we use S bar, we're going to get 0.009. Okay, so this is slightly bigger, slightly bigger compared to estimate S bar. Okay, so sigma cap is slightly bigger because we have this correction factor, which is C4. All right. Okay, I stop here for 10 minutes. Come back at 12:02. Is it okay?
Yeah.
Okay, so we take a break now. Okay. Okay. You see the screen now? I'm sharing the chart for X bar and R chart. Okay, let me show this again. Hello, do you see or not the screen?
No.
Okay. What do you see on the screen?
Just
Not seeing anything, Doctor.
Okay, about now, you see anything?
Same like just now.
Same. What now? Is it okay? Still cannot see?
Still cannot see.
What happened now? Let me close it. Oh, dah hilang macam mana ni? Share content. Okay. Okay, you see now?
Yes, example 6.4.
All right, very good. Okay, so we go back to the same example. Okay, now the issue is what happens if we have variable. Here we have variable sample size. Remember that earlier we have sample size of 5, right? But now there are situations where sample size is not constant. Okay, so in this case, we still can use X bar S chart. Okay, if we look at this example here, and this is 1, 2, 3, 4, 5. Okay, so the first subgroup here we have 5. Okay, we have 5, but the second subgroup we only have 1, 2, 3. We don't have sample number 4, number 5. No sample. Okay, but still we can calculate the X bar and S. This we can calculate, but now it's not consistent. This is n equal to 5. Okay, in this case n equal to 3. Okay, the next one is again at n equal to 5. Okay, if you go to this one, you don't have this number here. So this one n equal to 4. Okay, how do we handle this case? Okay, how do we handle this case where sample size is not constant? Okay, sample size is not constant. So this is what this example 6.4 is trying to show. Okay, variable sample size. Okay, so the sample size vary from 3 to 5. Okay, so we can use the procedure earlier, okay, to set up the X bar and S, but we have to recalculate again. Okay, recalculate again the X double bar because now it is going to change. Okay, so the grand mean and weighted average standard deviation are computed. Okay, using the earlier formula. Okay, so we have to have now not only all 5. There are 5, there are 3, there are 4, and so on. So we have to recalculate again. So now the total sample we have taken for this is only 113. Okay, 113. Earlier it was 25 multiplied by 5. You're going to get, originally it was 125, right? 125. Originally 125, but now the remaining only 113. Okay, the summation 113, and the total here also different now. Okay, so we get a new center, but luckily I think the center is the same. Just for the sake of example, I give you the same number, 7401. Okay, 7401 happen to be the same to make it easy. Okay, but anyway, the procedure is important here. We just follow the procedure. We have to calculate the total based on what we have. Okay, the total what we have. So in here they call it to get the X double bar, 5 multiplied by 74, 3 multiplied, because they are getting this number, average. But you can also just summation of everything also can. Summation of all the numbers and then divide by 113 also can. Okay, also can. So this way they put it 3 multiplied, I think 4. No, sorry, this is 5. 5 multiplied by 74.01. 3 multiplied by 73.996. So this is already taken the average. Okay, so there are several ways of doing it. Okay, so this is, don't confuse. But the inside here is the averages. Okay, the average. So finally you get this X double bar. Okay, X double bar. Okay, same thing also for S bar. Okay, so the S bar, we just recalculate again the remaining data that we have. Okay, there are 5, there are 3, and so on. Okay, so this is a new one. And then put it into the formula. Okay, for X bar chart. This is for the X bar chart. And this is for S chart. Okay, this is for X bar chart. This is for S chart. Okay. So okay. So now when we plot, okay, you may see that there is differences than the earlier one. What do you observe in this chart? This is using variable sample size. What do you observe here? Variable sample size. How is different than the earlier chart? You notice anything?
The dash.
Okay, you have here is the dash. The dash here is actually showing control limits. Okay, so it's very tedious to have control limit for every sample. Okay, so the dash actually is showing the control limit. So this is upper control limit. This is lower control limit. So you see that every sample here have this control limit, this control limit, this control limit, this control limit. See? So this control limit. So every sample has control limit. Same thing also here. Okay, in this case, as chart, as I mentioned earlier, upper control limit is more important. Okay, lower control limit is not important because the lower you go actually is the better, because this is dispersion. You want a small dispersion. We concerned about upper control limit. Okay, so this is control limit for sample number 1, for sample number 2, sample number 3. This is very tedious unless you put it in computer. Okay, for variable sample. So there are two ways of handling this. One way is we take individual. Another way is we take n average. Also can. We take n average, and this n average will be used in the formula. Okay, another method. One method is do it individually. Another method is take the n average. Okay, another method is take n average instead of n individually. So if you take n average, okay, you may have just one line. And also here maybe one line. This is coming from n average rather than n individual. Okay, rather than individual. So you see how tedious it is here. Okay, variable sample size. You're going to have lower control limit, upper control limit. Okay, for individual, see it's different here. But put on computer is okay lah. Just one button press. Okay, one button press is you can get all this control limit. But if you want to do it manually, okay, maybe take half an hour just to calculate this. Okay, same thing also here. Okay, that's why you get what you say a dash. Okay, the control limit now look like a dash. Okay, so this is the case where control limit is used. Variable control limits. What do you call it? Variable sample size. Okay, so an alternative method that I mentioned just now is using average sample size, which is n bar. Take an average or n bar, n average. So instead of calculating individually, for every sample have their own control limit. So you take the n average and use that n average in calculation of control limits. Okay, so using variable width of control limit and x bar and s control chart is to base the control limit calculation on average sample size n. Okay, control limit calculate based on n here. Okay, so if and I are not very different, this approach may be satisfactory. Okay, what it means that if we have 4 or 5, not much different, we can take the average. But what happens if the n is, there are some n equal to 4, another n is 10, another n is maybe 15. So this is very big difference. So this is not advisable to use average. Average is good if the sample size are not much different. Okay, not much different. So since average sample size n may not be an integer, useful alternative is based on approximate control limit. Okay, So sometimes you may not get, when you take the average, may not get a round number. Okay, so you can use it integer number, which is as approximate, okay, for the sample size. Okay, so we use approximate control limit. So this is to simplify the preparation. Okay, so in the case of S, you can use this formula, estimate the value of sigma. Okay, which is the sigma is the estimate of S average divided S4, C4, as what we have seen earlier. Okay, there are other chart, S2 chart. I'm not going to cover on this S2 chart. Okay. There are also short control chart for individual measurement. Okay. So, okay, any question before I move to, okay, before I move to this individual measurement, I would like to explain on the pattern and synthesizing rule. Is there any question on S bar chart, X bar and S chart? Are you following me or everybody is sleeping now? Hello? Okay, Adriana Ardini. Okay, what you learned today? Dengar tak ni? Okay, Khairil Ikhwan.
Yes, Doctor.
Okay, what do you learn today?
Today we learn about average run length and its formula, where ARL not is when the process is stable and no false alarm. And also when we got the ARL, we can find the average time signal or ATS and individual unit sample. And we also learn about the S chart, the revised chart. As usual, we need to have two phase, which is trial and revise. Now also S chart related to S chart.
Okay, very good. And also just now we learned about variable sample size in the case of S chart. Okay, before I move to individual, I need to emphasize this again. Okay, please read the e-books. You already have all these e-books. Okay, interpretation of X bar and R chart. Okay, let me highlight these patterns. Control chart. Interpretation of control chart. Okay, interpretation. Last week's also I touched a little bit, I exposed to you how the quality 4.0, what you call this, industrial 4.0, the use of new technology, for example, pattern recognition in recognizing process variability. Okay, before that we need to understand, okay, patterns in control chart. Okay, patterns in control chart. So what we call non-random pattern. Okay, non-random pattern. Okay, so what are the non-random pattern that we have? We have cycle pattern or cyclic pattern. Okay, these are common pattern. Common pattern where you are using control chart. Okay, what I meant is when you have control chart, okay, the pattern of the process might be fluctuating. Okay, it is within control limit, okay, but it's fluctuate like this. So if we connect the line, it just look like this. Okay, so this is showing something. What happened to this? Possible reason for this is, okay, it is going to cycle, is due to perhaps the maintenance schedule already arrive that we need to do maintenance, or maybe operator, the workers already get fatigued. Maybe in the morning he's working very well, in the afternoon his performance is down. Okay, or also maybe tool wear. Okay, tool wear. So okay, systematic variability. Okay, for example, maybe due to on-off cycle. Okay, on-off cycle. Sometimes it is a cycle is in good situation. Sometimes it is out of the regular setting, so it's going to show cyclic. Or also can be cyclic due to temperature change. In the morning, maybe okay. In the afternoon, it's going to be hot. Okay. Toward the end of the day, it's going to cool down again. Okay. Or maybe something is losing. Loose. Okay. Loose in terms of component, which is joined. For example, you join using okay, maybe using screw, or maybe using anything that can join two parts. Okay, so the cyclic showing that is that component, the mating part is wobbling, for example. Okay, we may also have mixture, also can also have shift. Okay, there are contribute by different source. Okay, so graphically we can see here. This is within control limit. Okay, control limit, within control limit, but it is showing like this. It's showing like this. So this is cycle. So what causing the cycle? Okay, as I say just now, there are possibilities. It could be fluctuation in temperature. It could be something is losing. Okay, the joint is loose, so need to tighten again so that that wobbling is going back to the original state. Or maybe mixture. Mixture is when you have, for example, two material coming from two different suppliers. One supplier producing this, another supplier producing this. So you may get a mixture pattern. Okay, this is showing the mixture of this part, and this also mixture of this part. Interpretation of this process variation is very useful because we want to make correction. If we get the right root cause, and then we can solve the problem. If we wrongly interpret, we cannot solve the problem. Okay, this one is showing the shift. Okay, the process is shifting. You see here there is a group of variability. This is another group. Okay, so what it means that if we take the average, this is one average, this is another average. So in this one, it is shifting. Okay, shifted to here. Okay, a shift happened. So what are the possible reasons for this shifting? Okay, this shifting could be change of method. Okay, maybe the workers that is operating in the morning change to another new workers. So changing the workers create a shift. Okay, maybe due to material. Okay, it could be to the machine, and there are many possibilities. And also shift also can be due to broken. A tool is broken. Suddenly you can see there is a shift in the pattern. Okay, could be broken tools. Okay. Okay, what happened to the trend? Okay, the trend is easily described when there is worn out, gradual wearing out. Okay, house lah ni mana? Deterioration. Okay, the tooling is deteriorate. Okay, so slowly deteriorate. House berlaku, kehausan berlaku, slowly deteriorate. Okay, so making that diameter that we produce getting bigger and bigger and bigger. Okay, so a trend like this. Okay, sometimes the trend also can go down. Okay, the trend is moving down. Why we need to capture this trend? Because before it hit the control limit, we should stop the process. And that is important to identify the control limit. So before this, we studied that 1 point out of control limit, but actually it's not enough to monitor process variability only based on 1 point outside control limit. We also need to see unnatural pattern. So we call this unnatural pattern. Unnatural pattern. If the process is stable, the pattern is natural. If the process is unstable, we call it unnatural pattern. Unnatural pattern is contributed by assignable cause. Okay, we call this assignable cost. There are assignable costs contributing to unnatural pattern. And assignable cost is cost that we can determine lah. Kita boleh cari ya, kita boleh cari assignable cost, and we can eliminate the cost. Okay, assignable cost. Another cost is we call it random cost. Random cost we cannot eliminate. Okay, it's there in the process. So understanding of this pattern is important. There is a pattern also, we call it stratification. Okay, stratification is normally very close to the center line. Okay, stratification. Okay, so this is example of stratification pattern. Okay, this is control limit, this control limit. So stratification happen very close to the center. So it looks good. Actually, the process is having problem. Okay, it is look very good because it is far from control limit, but it is not showing a natural variability. Okay, so if we continue having this, okay, at the end it will create a bigger problem. Okay, we call this method of pattern. This pattern is stratification. Okay, stratification. So where it's cluster artificially around the center. Okay, cluster artificially, it means that something is pushing this process to be on the center. It could be built out of, maybe in machining, the build up of the waste material stuck to the cutting tool. The cutting tool got stuck. Okay, got stuck, and then finally it might create overheated and then broken. Okay, it doesn't fluctuate up and down naturally, but artificially it looks like good. But after some time, build up of the waste material on the tooling and then get hot and then finally broken. Okay, so we need to know whether this is natural variation or unnatural variation. Okay, it can be misleading. Can be misleading. It looks good. Actually, it is artificial only. Okay, so artificial around the center. Okay, so we know that there is mark of lack of natural variability. Okay, we want it natural variability. Okay, so in case of stratification, it is not natural. It's not natural. So okay, any questions so far? So okay, this can be automated. Okay, we can use automated to recognize this because our eyes cannot detect this pattern, especially in automated system. So in automated system, okay, we need to use computer to recognize this. So we can have it, okay, like automated SPC, smart SPC, or we can even use artificial intelligence to train. Okay, artificial intelligence can be used to recognize this pattern. Okay, for example, using neural network. Okay, maybe industrial or mechanical engineering student may be not so familiar with this. This is, we borrow the techniques in computer science. Okay, use artificial intelligence to recognize pattern. Okay, to recognize pattern. For pattern recognition. Okay, you see nowadays people are talking about Industry 4.0 using AI, okay, using robotic, using internet. So this is one of the application of AI in quality, recognition of patterns. They also can use AI to recognize shapes, they recognize different features of products for visual or vision inspection and so on. Okay. All right, any questions so far? Okay, related to this variability, we did control limit. I did mention last time about synthesizing rules. Yes, synthesizing rules. Somewhere here. Okay, let me search where is synthesizing rule. Or sometimes we call it runs rule. Runs rule. Synthesizing. Or sometimes Western run rule or Nelson. Okay, Nelson's runs rule. Okay, this is Nelson's runs rule. Okay, also can be used. Okay, Nelson runs rule. Okay, runs rules. Okay, runs rule also a method that we can use to recognize variability within control limit. Okay, so to detect unnatural variation. Okay, unnatural variation. Okay, unnatural variation within control limit. Within control limit. Okay, when I say control limit, I'm referring to upper control limit, okay, lower control limit. Okay, so the rules is we call it in your ebooks, they call it synthesizing rule. Okay, this is like runs rule, same, huh? Runs rule or synthesizing rule. Okay, so this we use this rule why to make it more sensitive. Control chart become more sensitive having synthesizing rule. Okay, more sensitivity. Okay, so there are Nelson runs rule. Okay, this is some variation of rules. Huh? Nelson runs rule. There are also we call it Western electric runs rule. Okay, so what happened in this runs rule? Okay, there are okay, I'm not sure why it's not here, but I think there is yeah, there is rule. There is rule here. Okay, synthesizing rules. Okay, Western electric runs rule. So there are overlapping, some because different researcher, scientists, they come up with a different set of rule, but in this book, they compile it, make it synthesizing rule. Okay, the easiest rule that we use so far is one or more point outside control limit. So what happened is we have this control limit, upper control limit, and lower control limit. Okay, in this rule only, okay, in this rule only consider one point outside control limit, only this outside. Okay, this is rule number one. Rule number one. But actually, there are more rules, but the rules is considering a point inside. Okay, a point inside. Before this, I say there is a pattern. Also, can we use that to identify unnatural variation? But we can also use runs rule when the point is inside. Okay, when the point inside, we also can use runs rule to see unnatural variation. Okay, to see unnatural variation. Okay, let's see rule number two. Rule number two is 2 of 3 consecutive point outside the 2 sigma. Okay, this is the meaning here is we divide this. Okay, let me exaggerate here a little bit. Okay, let me put a bigger area. Tak boleh campur pula. Okay, tak apa. Okay, anyway, okay, let me change the color to make it clearer. Okay, if I use blue, okay, let's say I have this line, okay. Remember, 3 sigma above, 3 sigma at the bottom. So if this is 3 sigma, this dashed line will be 2 sigma. Sometimes they call it a warning line, warning, amaran. And I have another one here. This is, wow, hilang pula. Okay. Okay, just straight line lah senang. Okay, this is 3. This is 2. I have another line here. Okay, this is 1 sigma. Okay, the same thing also we divide the line into 3 at the bottom, 3 at the above. Here is central line. So this is 1 sigma, 2 sigma, 3 sigma. Okay, rule number 1 is clear. Rule number 2 says 2 of 3 consecutive point outside the 2 sigma warning limit, but still in control limit. So meaning that you have 2 points like this, 2 points. Maybe the earlier point is here. So 2 points outside. So when you connect here, you have this line, this line. So 2 points here. So out of 3, 2 points outside the 2 sigma. So this also showing that process is unstable. Okay, process is unstable. By looking at 3 points, we can say that the process is unstable. Okay, provided that it is 2 points beyond 2 sigma. Same thing also might be happening here. Okay, this 2 sigma maybe out of 3 points. Okay, earlier point maybe here, and 2 points is here. Okay, so this also showing a process is unstable. This is rule number 2. Rule number 3 says 4 of 5 positive point beyond 1 sigma. Okay, beyond 1 sigma. So we have 1 sigma is here. So from 5 points, okay, let's say I change the color here. Okay, out of 5, okay, you have 1. Okay, you may have another point here. You have this point, this point. Already 1, 2, 3, 4. Okay, this one not yet, not yet, because you need 4 of 5 outside beyond 1 sigma. So beyond now is only 3. So if you get one more out of 5 points here, okay, 1, 2, 3, 4. So the process also unstable. Okay, this is what is we call it runs rule or synthesizing rule. Okay, rule number 4, a run of 8 consecutive points on one side of the center. Okay, this is center. If 8 points is one-sided, is also considered as unstable, or maybe the upper side or lower side. Okay, so 6 points in a row steadily or increasing or decreasing. Okay, if you have 6 points steadily, let's say it's steadily moving down. Okay, let's say this point. 6 points. Keep moving down. Okay, so this also unstable. Or if you have 15 points in a row in zone C, which is both above or below the center line, 50 points in a row in zone C. Okay, we divide this into 3 areas. We can have this. Okay, we divide this into zone. Okay, let me see the leveling of the zone. Okay. Okay, the labeling of the zone. I hope I have this diagram. It's not here. Okay, I can just easily Google this. There's a lot of material on this. Okay, if you Google, you can see this run through, run through. Okay. Okay, let me find the right one, the clearer one. Run through, answers run through. Okay, do you see what I'm sharing now? Hello, nampak tak?
Nampak Dato'?
Okay, so you see here, okay, how this, all the point is inside control limits. You see here, you have this zone A, zone C. We have zone A, test A, B, C. A, B, C. Hold on. I think that one is not so clear. Okay, there is a diagram showing that how you can divide into this area. Okay, I think this one is a bit blur, but it is explained what I have just shown just now. Boleh nampak this line, this chart?
Nampak tu?
Okay, so you see here, okay, this is center line, this is control limit kan. So when you have 3 point, okay, beyond 2 sigma, so macam saya tunjuk tadi lah, 1, 2, 3, dua berada di above 2 sigma. Okay, this is considered unstable process. This is rule number apa tadi, nombor 2 ke? This is rule number 1 kan, 1 point greater than this. So another point tadi, 4 out of 5. Okay, 4 out of 5 above 1 sigma. Okay, dalam case ni lah. 1, 2, 3, 4, 5. So above 1 sigma, this is 1 sigma region. But this is 1 sigma, this is 2 sigma, this is 3 sigma. So you have 4 point, 1, 2, 3, 4 out of 5. So process also unstable. Okay. The other rule says that 8 point above central line. So this is central line. 1, 2, 3, 4, 5, 6, 7, 8. Okay, more than 8 lah. Dalam case ni dia nak 8 saja. Above, dia tidak, kalau natural fluctuation dia mesti ada atas dan pergi ke bawah. Ke bawah central line ni, 1 point go up and then go down. Okay, up, down, up, down. They cannot be more than 2. Okay, if you have 2 continuously, okay, macam ni, it's already unstable. So the point should go down, okay, to the other half of the control limit. Okay, so this also happened in this case, 8 point, but on the one-sided. Okay, on the one-sided. So some rule, some diagram is divided by A, B, C macam tu. Tapi in this case dia divide by 1 sigma, 2 sigma, 3 sigma. So A, B, C is only just labeling lah. Okay. Yeah, this is the one that labeling using A, B, C. Okay, instead of label this A as 3 sigma, dia kata this is zone A, this is zone B, this is zone C. Okay, zone C, zone B, zone A. Okay, is it clear on this? How we can use runs rule, how pattern can be used to recognize unstable process within control limit. Is it okay? Hello.
Okay, doctor.
All right, good. Okay, so I think our time also finished. So before I end, okay, I would like to hear from you, okay, whether you understand or not what I discussed today. Okay, can we have Fatihah? Fatihah, okay, what do you understand from today's lecture? Adakah Fatihah? Nama ada ni, orangnya ada tak? Okay, Arya Rafi Supatro. Okay, what you learned today? Can you summarize? Okay, anyone, please help me. Okay, to summarize what you learned today.
Can I, doctor?
You dah banyak kali kan? Minta orang lain.
Boleh.
Okay, bagi chance orang lain. Okay, Faiz, ada Faiz. Okay, okay, Faiz.
So for today, I learned about the S chart,
Okay,
and also when we have variable samples, we have